Welcome everyone, my name is Gusakova, and in this video I would like to present some results from our joint work with Christoph Tähle from Ruhr University Bochum and with Matthias Reisner from Osnabrück University. I would like to talk about two models of random polytopes, namely random polygone in a polygon and the so-called random convex chain. I will consider central limit theorems for the number of vertices of these random polytopes. And let me start with the first model. Let P be a convex polytope, d-dimensional, and let x1 to xn be independent random points uniformly distributed in P. We consider the convex hull of those random points, Pn, which is a random polytope. There are different functionals one can study for this random polytope Pn, but in this video we consider the number of I-dimensional faces Fi. In particularly when I is equal to 0, we consider vertices of Pn, and when I is equal to 1, for example, we consider edges of Pn. So what is known so far? So far we have the asymptotic formula for the expectation of number of I-dimensional faces Fi, and we also have upper and lower bounds of the same order for the variance of Fi of Pn. But the asymptotic formula for the variance is not known so far, and in general case it's quite complicated question. We also have a central limit theorem with a speed of convergence, but the speed of convergence contains factor log n, which is believed to be not optimal. Optimal would be some constant here independent of n. We are interested in planar case when d is equal to 2, and in this case these formulas can be made a bit more precise. So for expectation we still have asymptotic formula, and we also have asymptotic formula for the variance in compared to general case. The central limit theorem in two-dimensional case was proved by Kroneboom, but he didn't give any speed of convergence. He just proved the central limit theorem, and speed of convergence can be seen from these results of Parany and Reisner, and as I said already, it contains this log factor. It should be also pointed out that in two-dimensional case the only interesting functional is the number of vertices, which actually coincide with the number of edges. Our aim is to remove this log n factor, and that's our first result. Let P be a unit square, and then for Pn we have the following very thin bound, and the speed of convergence is believed to, or we believe it is optimal. Above we have some constant independent of n, and here square root of log n is exactly the order of square root of the variance of f0 of Pn. And the above bound holds for any convex polytope. The idea of the proof is based on the work of Kroneboom and on his approach for central limit theorem. I will talk about proof at the end of this video, and let us first consider what was the idea of Kroneboom. Let Pn be a planar convex polygon in some polygon P, and there are two very important observations about Pn. First one is that the vertices of Pn are concentrated near the vertices of mother polygon P. And the second observation is that the amount of remaining vertices is of order log n, which is very small in compared to square root of variance, so square root of log n. That's why for proving central limit theorem we can forget about these vertices and only consider those who are lying near the vertices of mother polytope P. And in particularly it is enough to just consider those vertices which are lying on this convex chain. And the remaining vertices are included in this log n. And now the question is how to analyze the number of those vertices, and Cronenboom has built a connection of those vertices with the jumps of some stochastic, pure jump stochastic process, and then he proved the central limit theorem for the jumps of this process. This is very technical and complicated approach. That's why at some point Buchter thought that maybe one can just consider this random convex chain as a separate object and study the number of vertices of this random convex chain. This leads us to the second model we would like to address today, is a random convex chain. Let T be this right triangle with these vertices, and let x1, xn be independent random points uniformly distributed in T. And we consider the convex hull of those points x1 to xn together with points 0, 1, 1, 0, which are vertices of T. And the function we study here is the number of true vertices of Tn, which means all vertices except for the vertices of this original triangle T. So the specific convex polygon is called random convex chain. And I would like to mention that it is enough to consider this fixed triangle, since all triangles in R2 are equivalent up to affine transformation, which does not change distribution of this functional n and small. So what is known so far for this random convex chain? Buchter managed to derive an explicit formulas for the distribution of Nn, and well, these formulas can be written explicitly, but the sum is still very complicated to evaluate and to actually see what those probabilities are. But nevertheless, Buchter also managed to obtain a recurrent formula for the moments of this random variable Nn, and from this recurrent formula he derived this asymptotic formula for all moments of this random variable. Natural second step would be to study central limit theorem, and that's exactly what we do by studying first probability generating function of our random variable Nn. And for this probability generating function, we derive the three-term recurrence relationship. And this three-term recurrence relation is exactly the one which corresponds to the orthogonal polynomials. Namely, it means that family of probability generating functions Gn von z is a family of orthogonal polynomials. And from the classical properties of orthogonal polynomials, it directly follows that Gn of z is a polynomial of degree n with n distinct real negative roots R1 to Rn. And again, from this fact, it directly follows that this random variable, or the number of vertices of Tn, can be represented as a sum of independent Bernoulli random variables with these parameters 1 over 1 minus Rk, where Rk are roots of probability generating function. And then applying the standard tools, we can also obtain a very standard tools for the sum of independent random variables. We also obtain a very affine bound for this number of vertices of Tn in the following form, which again we believe is optimal since this is a constant C independent of n, and here we have something which is of order square root of variance. Now, as I said at the beginning, I would like to sketch the proof of our theorem 1 about the very affine bound for the number of vertices of random polygon in a polygon. And the first natural step or needed step, standard step, is so-called Poissonization. It means that instead of Pn, we consider a convex hull of Poisson point process in this polygon P with intensity n. And those two objects, Pn Poisson and Pn, the distributions are very close to each other and the error is much smaller than this value here. That's why we can do it. And this is needed because now for this P-n Poisson, we can indeed study its behavior in the separate corners of P, and this would lead us to some independent random variables. And as I said before, we would like to use the approach of Groningen and somehow reduce the problem to random convex chains. But the problem here, we can't just directly apply the construction of Groningen because we will still have some log n remaining vertices and they would appear here. We would like to have a constant here instead. That's why we introduce the following construction. For each edge of square P, we choose some vertex zi, which is the closest to this edge. Then based on this vertex points zi, we build 4 right triangles, delta I, and in each triangle we have a random convex chain T of delta I, and due to this properties of Poisson point process, these convex chains are independent. And now our number of vertices of P and Poisson is just the sum of number of vertices of these 4 convex chains. And what remains is to glue together very affine bounds for these convex chains together. Some more results about random convex chains can be found in this article, and we are still working on very affine bound for random polygon in polygone. Thank you very much for watching this video.